Okay, so lots to think about there in terms of the types of calculations we'll see with equilibrium. Although, just to kind of reiterate, um, to very blunt effect, there's really two problems there. There's one where you're solving for Q, and there's one where you're solving for missing information, either K or concentrations. And I think that will help as you approach the problems. Really, to get a good grasp on how to do these problems, you just need to practice them. So a few more practice problems, either the problems from the textbook or the ones from the worksheets, I think will help you get a handle on this. And keep that in mind if you solve for Q or you're going to do an ice chart. That ice chart is always going to be the basis of these problems. Now, the last thing I want to talk about in chapter 14 is sort of a more qualitative approach to equilibrium. And this involves if we have a system that's at equilibrium, but something happens to change that, some kind of disturbance happens, we want to be able to just qualitatively evaluate, what's going to happen? Is it going to go and shift toward the products? Is it going to shift back toward the reactants? Or is that change not going to affect the equilibrium at all? So this doesn't have the kind of calculations that we just looked at. We're just really trying to evaluate what's going to happen when this disturbance occurs. And this is governed by what is known as Le Chatelier's principle. So I have it stated here in the notes, but let me read through it just for clarity. If a chemical system at equilibrium experiences a change in concentration, temperature, volume, or partial pressure, then the equilibrium shifts to counteract the imposed change and a new equilibrium is established. So basically what we're going to want to do is look at an equilibrium and then look at different changes and just try to use that to predict, is the equilibrium going to shift toward the products or forward, or is it going to shift toward the reactants or backwards? And Le Chatelier's principle is how we'll do that. Whatever the change is, the disturbance is, the system is going to try to introduce the opposite effect. So if something, some concentration goes up, the system's going to want that concentration to go back down, etc. So I have two examples here, and let's just go through the examples, and then you should have a fairly good idea of how all these issues are related. So here's our equilibrium. 2 moles of SO2 plus a mole of oxygen gives 2 moles of SO3, right? And we've got several things here that could happen to this equilibrium. We want to evaluate the changes. Now, the easiest one is concentration changes, and direct partial pressure changes would fall here as well, because those are the most straightforward to see. So if we look at part A, it says oxygen gas is added to the system. So if this system is at equilibrium, we add more oxygen gas. That means the concentration of O2 is going up, or it could also mean the partial pressure of O2 is going up. That's the disturbance that our system is going to counteract. So if concentration of O2 is going up, our system wants to do whatever would cause O2 to come back down, and that would be taking some of the O2, combining it with SO2, and making the product. So adding more of a reactant is going to shift the equilibrium forward toward the products. Okay? So it's going to shift to the products. Now let's actually go down to F, since F is similar. SO3 is removed from the system, so SO3 is the product. If we remove the product, the system's going to want to do the opposite. It's going to want to reintroduce product, and the way it would do that is by shifting forward toward the products. Right? So whatever you remove, the system's going to try to bring it back, fill that missing material back in. Whatever you add, the system is going to try to remove or get rid of in some other way. So the other ones are a little, maybe slightly more complicated. So let's go back up to B. B says the reaction vessel is heated. Now, when you look at these problems, you'll often have one of our old favorites, the enthalpy of the reaction. And enthalpy is important here because whether the enthalpy is positive or negative, you'll get a different effect by heating the reaction. The way I like to think about temperature changes or heat changes is I like to think about heat as a component of the equation. In this case, the enthalpy is less than 0. That means it's negative. That means this is an exothermic reaction. So we could think about heat as a product of the reaction. So if you can identify heat as either a product or a reactant, then adding heat or increasing temperature would be equivalent to increasing the concentration of that reactant. So in this case, if we heat the reaction vessel, we're adding more heat. If we add a product, the system wants to remove that extra product, and it would do that by shifting back that way toward the reactants. Right? And it would be just the opposite if this was an endothermic reaction. If this was an endothermic reaction, if delta H was a positive, that would mean heat's on this side. That would mean adding heat would cause the reaction to go forward. So when heat or temperature is changing, you need to know whether the reaction is endothermic or exothermic and what that means in terms of heat being produced or heat being one of the reactants needing to be added for the reaction to happen. Okay, part C, the volume of the reaction vessel is doubled. Now, what makes this one a little trickier is it's dependent on how many moles of gas are involved in the reaction. If we have one side of the equation with more moles of gas, that side's going to be favored in larger volume containers, and the side that has fewer moles of gas is going to be favored in lower volume containers. If we have the same number of moles of gas on each side of the equation, then changing volume won't change anything. So we look at this reaction, we've got 3 moles of gas on the reactant side, 2 moles of gas on the product side. So that means smaller volumes would favor the products, larger volumes would favor the reactants. So the volume is doubled, that means a higher amount of volume. That's going to cause the reaction to shift toward the side where there are more moles of gas. So this would cause a shift to reactants. So counting how many moles of gas are involved is important for this type of analysis. Now, part D says a catalyst is added to the mixture. We talked about a catalyst back in the last chapter on kinetics. And in fact, what a catalyst does is it changes the pathway, so it can cause a reaction to be faster, but it doesn't change where the energy of the starting materials, reactants, and the energy of the products are. So an equilibrium is really a thermodynamic effect. It's affected by the energy of the products and the reactants, and a catalyst cannot change that. So the catalyst has no effect on an equilibrium. It might allow you to get to equilibrium faster, and if you have a system that's out of equilibrium, like a Q problem, you might reach equilibrium at a faster rate with a catalyst, but it will not affect the way the equilibrium is distributed in terms of materials. So it would not affect this reaction. And then part E, the total pressure of the system is increased by adding an inert gas. So we know we can write an equilibrium constant expression in terms of pressures. If the partial pressure of one gas goes up, then that's going to cause a shift that would try to bring that back down. If, however, we add an inert gas, that's going to increase the total pressure in the system, but it's not going to increase the individual pressures of the components. So this would also have no effect on this particular equilibrium. Okay, now if you added in a little more gas and that one gas's pressure went up, that would cause an effect, but just increasing the total pressure does not. Okay, let me go to the next page, see if we can get this last page in, and this particular video not be too long for me to post easily. So similar idea here. We've got a reaction, we've got its enthalpy. Now let's look at some of the important pieces of information before we go into the choices here. 4 moles of ammonia, 5 moles of oxygen, we've got 9 moles of gas on the reactant side, 4 moles of NO, 6 moles of water, 10 moles of gas on the product side. So more gas phase products than gas phase reactants. So that'll come into play when we look at things like volume. Delta H, it's kind of split the way the line broke, but it is negative 904.4. That's an exothermic reaction. So that means heat here is a product of the reaction as well. So any change to temperature or to the amount of heat added, we can think of what's that doing to a product of the reaction. Okay, so part A, increase the concentration of ammonia. That's a reactant. So if our disturbance is increasing that concentration, our system's going to want to decrease it, and it would decrease it by shifting forward, by taking some of those reactants and making them into products. increase the concentration of water, right? Water is a product. If that concentration goes up, our system's going to want to bring it back down. It would do that by the reaction shifting to make more reactants. So that would shift back toward the reactants. If we decrease the concentration of O2, somehow we're removing O2 from the system, we decrease this reactant, the system's going to want to bring that concentration back up. It will do that by shifting the reaction back toward the reactants to fill in that missing concentration of O2. Now, if we decrease the volume of the container in which the reaction occurs, that's going to favor the side that has fewer moles of gas. Right? As we compress the gas together, if the equilibrium shifts, it can better respond to that change in volume. So since we have 9 moles of gas on the reactant side, 10 on the product side, a smaller volume is going to favor the reactant side. So the equilibrium will shift, so there's less gas occupying that space. If we add a catalyst, that's going to have no effect on equilibrium. And you kind of need to see that one once, and you should get that one every time from there. And the last one, if we increase the temperature. Now, we did say it's an exothermic reaction. Heat is a product. If we increase the temperature, we're adding more of a product. And of course, our system wants to counteract that disturbance. So adding more heat would shift the reaction back toward the reactant side. Okay, that's the end of chapter 14. We'll move on to chapter 15.